ladies and gentlemen.
So let's talk graphs of polynomials. A reminder, a polynomial is a combination of terms with addition where all of those terms are a coefficient times x to some integer power. So again, we have a string here. All the coefficients are real numbers, and all of our exponents are non-negative integers, meaning no -1, no 0.2, or anything like that. All integers. We have some properties that are shared amongst all polynomials. First and foremost, the y-intercept is 0, z. Whatever the term that does not contain an x, that's your constant term, that's your y-intercept. That's where the graph is going to cross the y-axis. In addition, we have turning points. That's where the graph changes direction. It's either changing from going up to going down, or from going down to going up. The number of turning points we have is n-1. Well, that's the maximum anyway. We could have less. A little bit of weirdness with that, and that comes through experimentation, kind of figuring out what those patterns are. But you're always going to have, at most, one less than the degree of the polynomial. In addition, this is something a little bit weird that's not often taught. The sum of all of the zeros of a polynomial is equivalent to -b over a. So we've actually used this to figure out the x value of the vertex for quadratics, because we would just take the average, -b over a. When we have only two of them, the direct middle would be the average. And that's because quadratics have this beautiful symmetry that not every polynomial above degree 2, above a quadratic, is guaranteed to have. But every polynomial has all of its zeros sum to -b over a, which is very important and kind of niche for solving niche problems. We've already talked about this, but the axis of symmetry, the x-coordinate of the vertex, is x equals -b over 2a. And the end behavior of a polynomial, that means where does the arrows go at the end of the graph, is determined both by a combination of the degree, the highest exponent, and that term's coefficient. So let's look at that in detail. If the highest exponent, the degree, is even, then the ends go in the same direction. Either the ends go both up or they go both down. What determines that? The leading coefficient, the coefficient of that term with the highest degree. If it's positive, then the ends are going up. If it's negative, the ends are going down. Relatively easy to remember. The odd one is where we're going to have some trouble. If the degree, the largest exponent, is odd, then the ends go in opposite directions. And how do you tell which one's which? Well, if the leading coefficient is positive, if the number in front of the x with the highest degree is positive, the right side is going up and the left side is going down. So you can kind of think of it as the leading coefficient tells you what the right side is going to do. And if it's negative, the right side is going to go down. If n is even, they're going in the same direction, and if n is odd, they're going in opposite directions. Not too hard, but it takes a little bit to remember, and it's quite a lot of information to remember all at once. So, if we have this function here, where we have a degree 4 polynomial, and we're told that the leading coefficient is negative, and our constant, our y-intercept, is also negative, which graph could it be? Well, first and foremost, the degree is 4. We want the ends to go in the same direction because it is even, and all of the graphs meet that specificity, so can't really eliminate anything from there. We do know that the ends are supposed to go down because the leading coefficient is negative, so that means that A doesn't work and D doesn't work. Final piece of information, the y-intercept is negative, so it means where we cross the vertical axis should be on the negative side of the x-axis. It should be below the horizontal axis, which means that B is the only answer that works. So, not too bad there, just what is the end behavior, y-intercept, and all that. One last thing I want to teach you about is the remainder theorem. And remainder theorem basically means that if I were to evaluate a function, if I were to take f and I were to evaluate it at a, and I get b as an answer, that means that if I divided the polynomial f of x by x minus a, that it would have a remainder of b. So essentially we can see if a polynomial will divide nicely by plugging in what we believe the 0 or root to be, and if we get a 0 from that, it is a factor, and if it's not, whatever we get would have been the remainder from that. So how does that help us here? Well, we have a nice polynomial here, but we're missing the leading coefficient. We don't know what that is. It's an a, and we're trying to find it given that this is a 0, meaning that if I plug -3 in, it doesn't have a remainder. Its remainder is 0. So we're going to replace the p of x with a 0 and all of the x's with a -3, and the equation should be true given that this is a point. So we have a times -3 cubed minus 2 times -3 squared minus -3 plus 11. So -3 cubed is -3 times -3, which is a positive 9. Positive 9 times -3 would be a -27a. -3 squared is positive 9 times -2 would be a -18. Minus a -3 would be a plus 3, and then we have this plus 11. So let's combine our numbers, our constants together. We have a 14 here, so -18 plus 14 closer to 0, that would be a -4. So we have -27a minus 4 is equal to 0. We can add 4 to both sides, so we have 4 is equal to -27a, divide by -27, and we get a is equal to -4/27. So not too bad there, just really plugging in the value for the point and then solving for your missing number. The last one is where we need one of the tricks that we learned about above. So we have a polynomial, and it's a quartic. It is a degree 4 polynomial, and we're missing 2 values for this one. We have zeros at the points 6, 5, -1, and t. What is the value of t? Well, we can use this information, kind of like in the equation or the problem above, to find the missing values of the constants and then divide by all of the zeros that we know, but that is going to take a long time. What we can do instead is we can use the rule that all the zeros of a polynomial sum to -b over a. So in this case, -b over a would be a -26 over 3, which kind of simplifies down to be 26 thirds. 26 is not divisible by 3, so we're going to leave it like that, but we are going to add all of our zeros together. So not plus, but equals, Mr. Whaley, 6 plus 5 plus -1 plus t. So if we try to make this a little bit simpler for us, we can combine all of these constants, these numbers together. We have 6 plus 5 plus -1. That would be a 10 plus t is equal to 26 thirds. And what we can do, sounds a little weird now, I can multiply everything by 3, and that way I'm not working with fractions as much, and that might help some of you make the problem a little bit more simpler and easier to work with. So 26 thirds times 3 is 26. 3 times 10 is 30. 3 times t is 3t. We can subtract 30 from both sides, and we end with the -4 is equal to 3t. So divide by 3, we see that t is going to equal -4 thirds. So not too bad if you know the trick, but if you don't know the trick, it is a very long and tedious problem. Not necessarily overly difficult, just long and tedious, and if you're especially preparing for like college entrance exams or a timed test like the SAT, you're not going to have to spend all of that time doing all of that work. So I'll bring it back up for us. We do have all of these lovely properties of polynomials that you can take advantage of but only if you remember them. So good luck with any practice, and I'll see you in the next video.